Hello, my name is Chris Harris and I'm from Allery Chemistry, and welcome to this video on equilibrium and sustainability, and this is for the CI topic, or the chemical industry topic, for OCRB salters. So this video is dedicated to OCRB salters and that covers all of the information that you need for this exam board. So you might find other resources online, for example, that may be quite generic or have general information, and you're wondering if it actually does cover the specification, if it's right for you. This video, everything in here is dedicated to the CI topic, and so it's perfect if you are studying OCRB salters. And in fact, there's a full range of OCR salters videos on Allery Chemistry YouTube channel that goes through from year 1 all the way through to year 2. There's also a full range of generic videos as well, whiteboard tutorials online as well. So on Haber Chemistry, it's all for free. So all I would say is that you just hit the subscribe button, and that'll be absolutely fantastic. So there's I don't charge for these at all. Your subscription is enough for me, and as long as people keep subscribing and watching the videos, then I will keep making them. So also these videos here, these are the revision videos. One was the black background. These are available to purchase in my test shop. They're great value for money. The link is in the description box below. You can use them on the move on your smartphone or your tablet, and I've known people to print them off as well and use them as revision notes and annotate them, etc. So they're quite colourful, deliberately to make them as attractive as it can be. As much as I enjoy chemistry, I know for most it's quite a struggle, so to make it as bright and colourful as possible, and that just makes it a little bit tangible, I suppose, a little bit more bearable to actually to use them. So but they're available there, and you can go and have a look at them there. So this but the salters course, obviously this is just a part of the chemical industry. The way salters works, they break them up into topics like this. So it's CI, for example, oceans, elements in the sea, etc. So they break them up into these topics. So what I've done instead of doing one video for the topic, which would just take ages, I've broken it down into different kind of chunks. So this one's going to look at equilibrium and sustainability, but there are other videos within the CI family as well that you can look at, that if you see something that's not mentioned in here, then it might be in another video. Okay, so it is dedicated to the specification, as you can see there. So we're mainly going to look at equilibrium. We're going to be looking at equilibria KC, which you've seen in year 1. So we're going to look at that. And we're also going to be looking at sustainability as well. So there's a lot of that in terms of industrial processes and what makes something sustainable. Okay, so actually on the topic of sustainability, let's have a look at some mass-produced chemicals first, and look at how the chemical industry, because this topic is the chemical industry. So we're going to be talking about industrial processes. So we're going to be looking at how chemical companies can be financially economical, because when we're making drugs or pharmaceuticals or other chemicals, we've got to try and make sure that the chemicals that we're making or the drugs that we're making are sustainable. Okay, and with some key things that we have to consider here. So the first one is raw materials. Now, raw materials are obviously the substances that we need to make what we need to make. So that might be, for example, crude oil, it could be salt, it could be anything like that. So chemical companies will try and source raw materials as cheaply as possible, and they must be widely available, because if you're going to mass produce a chemical, you're going to need a large amount of your raw material. And so this means we have a sustainable supply. What we don't want to be doing is extracting minerals, say, from the earth, and there's a limited supply of them. Because then that would, if any of you study economics, you know that if there's a limited supply, it pushes the price up. And if the price is too high, it makes it kind of unreachable for most countries and people. So it's got to be a sustainable option, unless it's really going to provide some benefit, of course. So energy is another one. Obviously, during the manufacturing process, we have to obviously use energy to make the drugs or chemicals that we're making, for an end use. But also, we've got to think about transportation as well. So moving goods around the site. These sites, if you've ever seen, these large chemical sites. I mean, I live in Northumberland and Morpeth, so there isn't really many large chemical sites around here. However, about an hour and a half away from me, there's Teesside, and Teesside has a huge chemical village, yes, called Wilton, and it has some of the biggest chemical manufacturing companies in the world are based there, mainly because of the port. So it's easy to get things in and out of the port. And they congregate in one area because they supply chemicals to each other, and they make the everyday materials and products that we see today, whether it's drugs or whether it's the plastics, dyes, whether it's raw materials to make the things that we use. So these are vital industries and huge contributors to the economy. But the energy here, the energy needs to be kind of managed properly. We need to think about how we're empowering the vehicles to go around these sites because they're massive. We need to think about how we manufacture them, temperatures and pressures, etc. These all cost money. The other thing as well is overheads. Now, all companies have fixed costs. No matter what they produce, they'll have a fixed cost. That may be cost of land, for example. They may be renting the land. They may have to pay business rates, for example. They'll have a base cost for electricity and gas. They'll have staff. Staff need paid. So you have fixed costs. And so no matter how much product they produce, they still have to cover this basic cost before they even start make any profit before that as well. So there's various things there which can affect overheads. And then waste is another one. So waste from byproducts. Actually, waste costs money. You can't just dispose of things for free. You have to pay for it. So whether it's, for example, in domestic housing, you pay council tax. The council tax goes then to pay for waste disposal. And also the tip as well. But if you're commercial, like large companies like this, they have to pay a private contractor to dispose of their waste. And if the waste is quite hazardous, it's got to be specially treated. It can't just be thrown away as you like. So there's regulations put in place where companies have got to act responsibly when getting rid of any waste. But what a lot of companies do is actually being quite creative, and they produce products that they may not initially want, but they're produced anyway. For example, you may produce HCl as a byproduct. Now, HCl is classed as a co-product. In other words, it can be used for something else. So HCl can be diluted in water, and you make hydrochloric acid, and the company can then sell that as a co-product. So they can make profit from the waste as well. And it means that less waste. The lower your waste. Obviously, the lower the waste, the cheaper it is for the company. So there is an incentive for these companies to reduce waste because it costs less, and there's green tariffs and all sorts, to try and make sure these companies are behaving themselves. And reactions, like I say, this kind of leads into atom economy and percentage yields. Chemical companies try to maximize both of these because it reduces waste. It's better for the environment, and economically it's more sustainable as well. Okay, so just staying on the mass-produced chemicals side. So the conditions of an industrial reaction must be carefully considered to maximize profits. Okay, so the pros and cons are listed for each condition. So this is vital because all of this, when a chemical firm is making a product or a chemical or whatever it is, they've got to normally use pressure, heat, or they've got to use some form of catalyst to help the reaction go. So we're going to be looking at the pros and cons of these different types of reactions here, the different types of conditions. So let's start with pressure first. So the advantage with pressure is this is beneficial to gas reactions, as higher pressures speeds up the rate of the reaction. If you can produce your product quicker, it means that your time is being used more effectively and efficiently, and they say time is money. So if you're producing something efficiently, then your profit margins are going to be higher. However, the downsides with using with altering pressures is that high pressures means that gases need to be pumped into vessels, and these pumps cost a lot of money and use a lot of energy to actually install. Higher pressure systems means the piping around the site needs to be substantially more robust. It needs to be thicker. That costs a lot of money, and you've got the safety concern as well. You're handling or you're transporting around gases at high pressure. If there's any fracture or damage to any of these pipes, then that can cause serious problems because you can get huge explosions. So you need staff to go around and make sure and maintain the site and make sure that the pipes are, and pipes and vessels, etc., are actually up to standard to make sure that it is safe to operate in that place. So the other one is a catalyst. Now, the advantage of a catalyst is, as you may have seen, is that it allows reactions to run a lot more quickly, so that's good, and lower energy is needed, so because we don't have to heat it up as much, so the activation energy is reduced. And also with catalyst, we can reuse them. We can, once we've used it for batch number 1, we can then reuse it again to make batch number 2 and batch number 3, etc. So that's quite efficient. It means we're not getting rid of the catalyst unnecessarily. The downside, though, with catalysts is they are expensive. They're not cheap to install, so there's a cost associated with putting massive grids in with catalysts in the reaction vessels, and some catalysts that are in the same state as well. So you can get homogeneous catalysts. These have to be separated once the reaction is complete, and so that increases costs as well, because we've got an additional step that we have to heat that to get rid of it, or we have to have a particular part of the site to get rid of this the catalyst, and then we use it again. So it's not obviously it's not all good. Catalysts are clearly a good thing to use, and industry do use them, but we've got to weigh up the pros and cons of that. Okay, so temperature. Higher temperatures mean that the reaction is produced faster, so that's fine. More products produced per unit time, so that means we've got a more efficient plant. Productivity is high if we heat the reaction vessel up. This is because the particles got more kinetic energy, so they've got a much higher chance of them colliding and then collisions leading to a successful reaction. So a higher temperature is pretty good. However, the downside of this is that higher temperature means you need fuel to power up furnaces, or you need electricity. For example, if it's electrolysis, you need a large amounts of power to actually get this going, and so that is really expensive. So you need to know the pros and cons of each of these. It can be very easy to look at the advantages of these, because you think, okay, well, if we can make it faster, that's fine. But if it's so expensive to do that, then, and the drug that you're selling, or the chemical that you're selling, or the product you're selling really doesn't command a high price, and you've got competition as well. Obviously you've got competitors making these, you've got to try and make sure that you're making it as efficiently as possible, and you can cover your costs. You don't want to make a chemical that bankrupts your own company. Okay, so what we're going to look at, so we've looked at the different conditions, so we're now going to apply this a little bit to some of the core chemistry here. And so we're going to be looking at reversible reactions, okay? So you might have seen, in fact you will have seen reversible reactions in year 1 chemistry. So we're going to be kind of building on that, and you will have seen KC as well in year 1 chemistry. So we're going to be looking at some of the adaptations from the first year chemistry, and we're going to be building up into this topic. So reversible reactions are ones where, remember, where they go forwards and where they go backwards, so they're reversible. And so we represent them using this arrow here. So this is this reversible arrow, reversible reaction. And so a generic example would be A plus B would form C plus D, and vice versa. We can go forwards and backwards. So if we bring up a graph here, you can see that the forward reaction of this, so with this reaction here, you can see that we have a curve here, and the concentration is depleting quite quickly of our reactant. And this is obviously going to flatten out or plateau towards the bottom. So initially that's used up really, really quickly, and then obviously as your reactant concentration decreases over time, there's a less likely chance of these successful collisions, and so therefore the rate of reaction then slows down. So then likewise, if we go the other way, so the backwards reaction, so this is where again we're looking at our reactants. We have very little of our reactants, but over time the concentration of the reactants speeds up quite quickly, and then it flattens off. So this is going in the reverse direction. So this is going forwards, and this is going in the reverse direction here. Okay, so again we're looking at products reacting together. So the product side reacting together to form our reactants. Okay, so the point at which both of them start to plateau, which is here, then we say that, and in other words, the concentration of them are not varying, they're not changing, then equilibrium is reached. Okay, so we say that we call this a dynamic equilibrium. Okay, so the concentration of each of the substances remains constant. Okay, so the rate, the amount of it, and the amount of them here, the concentration is the same for each of them. What you can't get confused with is this is not the same as the amount of reactant and product is the same. So you might have different amounts of reactant and product at each of these phases here. However, the concentration of the substance remains constant. You've got to be really, really careful with the language that you're using, the words that you're using here. Make sure that you're being specific. The amount of reactant and product So the amount of the reactant product is not what we're looking at, the same amount. It might not be the same amount. There might be more product, more reactant. It just means the concentrations of each substance is constant. Okay, so what do we mean by a dynamic equilibrium? Well, dynamic equilibriums only happen in closed systems. So what that means is if we're undergoing this reaction or allowing this reaction to occur, then what we've got to make sure is that our reaction happens obviously in this beaker here. And you get products and reactants being allowed to react in here. Some may be quite volatile. They may evaporate quite readily. So what we want to try and do is trap any chemicals that are in there within that beaker, but also we don't want anything from outside entering and reacting in here, like aerial oxidation, for example. So it depends on the reaction that you're doing, but a closed system, it's really important. A closed system is a one in which products can't be lost and nothing can actually get in either. Okay. Right, so remember we'd seen in year one, in year one chemistry, when we looked at Kc. Okay, so we looked at the Kc topic, or what Kc is. So Kc is the equilibrium constant. So you would have seen that there. So what we're going to build up on in the chemical industries topic is we're going to be looking at the factors that affect the value of Kc. Okay, so you need to know the effect of temperature, concentration, and catalysts on this equilibrium constant here, and this is vital for the chemical industry, because if we can understand how we can change equilibrium, we can change the yield, and if any of these factors can have a advantage on that, and like a good effect, or might have an adverse effect. So let's have a look. So with temperature, Kc is only valid for one temperature. Okay, so changing the temperature will change equilibrium conditions, and hence Kc will change as well. Okay, so that will change too. Now with temperature, if the temperature change causes equilibrium to shift right, then Kc will increase, and if temperature change causes equilibrium to shift left, then Kc will decrease. Okay, so let's have a look at a specific example here for reaction. So you can see here that the forward reaction in this example here, we're making sulfur trioxide, okay, which is this. Now sulfur trioxide is really important because actually we use that to make sulfuric acid. So we react that with water and we form H2SO4. So actually the manufacture of SO3 is quite an important step in making sulfuric acid. So this step here, the forward reaction is exothermic. We can see because our enthalpy value is minus 197. So remember, a minus value, it's telling us that it's exothermic. Going backwards is endothermic, because if the forward reaction is exo, the reverse must be endothermic. So this is actually linked with Le Chatelier's principle, which you would have seen in year one chemistry. So Le Chatelier's principle is looking at what impact. So if you make a change to a reaction, then the reaction will try and oppose that change. So for example, if we increase the temperature, then the reaction will shift to try and decrease the temperature, and vice versa. So if we increase the temperature here, in this case, then equilibrium will shift in the endothermic direction to oppose that temperature, and Kc will decrease. Okay, so if we decrease the temperature, it will do the opposite. So equilibrium shifts in the exothermic direction, and Kc will increase. Okay, so how do we know that these will increase or decrease? Well, remember from our Kc expression, so our Kc expression is always products over reactants. So remember that from year one chemistry. So the products here are SO3 so sulfur trioxide squared. So remember the number in front of the number of moles in front of the molecule here is the power that goes on the top here. Okay, so in this case, this is going to be SO3 squared, and then we've got our reactants, which are O2 and SO2. So if you think about it as like a fraction. I know some people may not be quite good at maths. Some people may be really, really good. Some people might not be so good. So for those who are really good at maths, you probably spot this in, quite in an obvious way. But if you're not so good at maths, then I'm going to point it out and show you how it works. So you've got Kc, products over reactants. Product concentration increases. So imagine it like a fraction. Okay, so remember it's like 1 over 2. So 1 over 2 is a half, isn't it? It's 0.5. So if we increase that top number to 2 over 2, okay, then 2 over 2 is a whole, that's a 1. So by increasing the top number, we actually increase the actual factor here. This is Kc. And so likewise in a fraction, if we do 1 over 2 and if we increase the bottom number, say to 1 over 3, then that goes from 0.5 to 0.33. So by increasing the bottom number, we're dividing it by a bottom number, a larger number, then this value is going to decrease. So in other words, if we get an equilibrium where we're producing more reactants, then Kc will always decrease because they were increasing the bottom number. If Kc, if the equilibrium shifts to produce more products, then Kc will always increase. Okay, this number will increase because we're increasing the top number. So Kc will rise. So just see it as a fraction, just a standard, bog standard fraction. All we're doing is we're just putting in obviously chemical formula in there, but it is exactly the same. It's just a ratio. Okay, so we need to know. Obviously, we looked at the effect on temperature there, so we also need to know what it is for concentration. Now, with concentration, the value of Kc is unaffected by any changes in concentration, so it doesn't matter if we change any of them concentrations of our reactants or products, they are actually unaffected. And then if we look at catalysts, again, catalysts have no effect on the value of Kc, okay? So what a catalyst does, it speeds up a reaction, that's fine, but equilibrium is to do with yield. So a catalyst does not produce more product. All it does is it speeds up the rate at which a product is produced. Or in this case, if it's to do with equilibria, it speeds up the rate at which equilibrium is established. Okay, so it has no impact, very important, there's no impact on the actual equilibria process. Okay, so let's look at a specific example here, and we're going to look at obviously there's various factors at play here. We've got temperature, we've got concentration, and we've got pressure, which is linked with that, and we've got catalysts as well. So now we're going to kind of mix all these together and apply it to an actual tangible example. And here we're going to be looking at the Haber process, okay, because the Haber process is a very, very important industrial process here. So the position of equilibria is actually really important in determining the most economical method. So the Haber process is an example of compromises that are needed for our reaction. Okay, so let's have a look at the Haber process first. So here's the Haber process. So you can see it's the manufacture of ammonia, which is used in agriculture. Okay, so it's used as a fertilizer. So it's a vital chemical, and that's needed. Constantly. You need fertilizer to help grow crops, and we need crops to help keep humans and animals alive. So you can see here that we've got nitrogen plus hydrogen will form ammonia. The reaction is exothermic, delta H is negative. Okay, so what we're going to do is we're going to try and look at the different factors here, such as pressure, temperature, catalyst, etc. And we're going to see what impact that has on this reaction. So let's have a look at pressure first. So high pressure will favor the forward direction, okay, which means that you get a higher yield of ammonia. Okay, so the equilibrium shifts to the side with the fewest number of moles. Okay, and the reaction is also faster too, because if we confine these particles in a smaller space, they've got a higher chance of them colliding successfully if you put them in a small box. So it actually does speed up the rate of reaction as well. But you can see here, this is obviously a reaction here, which has got 4 moles on the left, 2 moles on the right. So if we increase the pressure, equilibrium is going to shift to try and decrease it, and that's the side with the fewest number of gas moles. So this is going to shift to the right. So we're going to produce, increasing the pressure means that we produce more ammonia, but at the same time, we also increase the rate of reaction as well. Okay, so high pressure systems though are expensive and they can be dangerous. So a compromise is established when we're looking at this, and actually, after a number of scientific calculations and trial and error, industrial process to make ammonia is normally around 200 atmospheres of pressure that is used for this. Okay, so we've got this compromise between cost and obviously yield as well. So let's look at the next one, which is temperature. So high temperature will speed up the rate of reaction as well. So as well as pressure, it will also speed up the rate of reaction because the particles will have more kinetic energy. But high temperatures will actually reduce the yield of ammonia. You can see here that this is an exothermic reaction. Okay, definitely exothermic going forward. So if we increase the temperature, the reaction is actually going to shift in the endothermic direction to reduce the temperature, so it will shift to the left. So actually by increasing the temperature, we're producing more reactant, which is obviously not what we want. So we have to come up with a compromise here, and the compromise is that a temperature of 400 degrees Celsius is used as established, but if you have a temperature that's too low, for example, then the reaction will be far too slow. So we can't just say, well, why don't we just do it at room temperature? Well, it would just take ages to make the product. Yes, we'll get a good yield of product, but it would take forever and a life to actually get that made. So that's not very good. So the compromise here is we use a temperature of 400 degrees alongside the pressure of 200 atmospheres. Okay, so let's look at the benefits and risks of chemical production here. So you need to know about the risks, but also the uses of chemical products that are used by society, okay, because we use them every day. Sometimes we forget about how these things are made. Obviously, we're just more interested in using them and getting benefiting from them. But these things have to be made from somewhere, and they're manufactured in chemical sites, globally, right across the world. But we have quite a large chemical industry within the UK as well. So domestic chemical industry is quite a booming industry, and like I said before, it contributes a large amount to the economy and it employs people, etc., etc. So we're going to look at the advantages and disadvantages of these industries here. So we'll look at the advantage first. So pharmaceuticals help prevent and cure lives. Okay, so this is a vital use, obviously, for pharmaceuticals industry, and we have numerous pharmaceutical companies. There's one here where I live in Morpeth called Piramal that makes pharmaceuticals. There's one in Cramlington, which is Merck Sharp and Dohme. You've also got GlaxoSmithKline and Barnard Castle. So you've got loads of, like, in and around this area where I live. There's some big pharmaceutical factories that that make these, and they're actually everywhere. They're kind of tucked out the way. You don't really notice them that much. The disadvantage is that some of these chemicals can be harmful to the environment. So this, for example, gases, pollutant gases can cause air pollution. If we've got forming solid or liquid waste that has to be disposed of properly, how is that actually disposed of? It's going to go into landfill. That could cause land pollution. You get leaching into the watercourse, etc. So another example is fertilizers. Now, fertilizers help to ensure food is produced in the most efficient way, so that's good. We've just seen that example there with the Haber process. A downside of chemical production is that some chemicals are actually flammable and explosive. So these are things like methane or alcohols, for example, is another one. And obviously these need to be stored and labeled correctly to make sure that they are being handled suitably. Another advantage is plastics have revolutionized the materials that we have today. Everything that I'm speaking through, this microphone, the stand that I'm using, the computer screens, the computer itself, keyboards and mouse, everything that you can see here, down to the router that's allowing it to be transported across to yourselves. Everything is being used to, plastics are involved in that as well as metals, of course, but plastics too. However, some chemicals are harmful to our health. So a disadvantage is they can be harmful to our health. They may be through inhalation or contact. For example, mercury or chlorine, hydrochloric acid, for example, or hydrogen chloride gas is a byproduct of some of these reactions. And you can get chemical disasters in a plant as well, can affect the surrounding population. So a UK-based example, classic example, is Flixborough down in Lincolnshire, where there was a huge explosion of a chemical plant, and obviously it had an impact on surrounding areas as well. So have a look at that if you are interested. But as a UK example, accidents do happen. Thankfully they're incredibly rare, but we've got to be really, really careful about what chemicals we're using and how they're stored. Okay, so another advantage, a final one here, another advantage is that dyes and cleaning products have actually helped to improve our living environment and lifestyle. So thanks to, some of the detergents that we have now, we don't even need to really boil our clothes now. They can be done at really low temperatures because of, the advanced formulation of cleaning products. We've also got products such as obviously the dyes that we have that's in our t-shirts, that we can get certain products which don't actually leach out. You can wash your clothes and it's not going to bleach. You're not going to bleed into other clothes very easily. So the advancement of technology is amazing, and all of these products, everything we see, touch, breathe, eat, sleep on is made through chemicals. So, it's a huge industry, as you can see. Okay, so Kc, the equilibrium constant. So remember we were looking at Kc before and looking at the equilibrium of these. So Kc are looking at the equilibrium of reactions. So Kc can be worked out from the molar concentration of a reaction. Okay, so remember we're looking at what Kc and what can impact Kc. So the molar values in front of each species, like I say, are the powers in a Kc expression. Okay, so remember when we write out Kc, we put products over reactants here. Okay, so these obviously the two values here is obviously the 2 that's in front of that. So we can see that our products are on the top, reactants are at the bottom, and square brackets mean a concentration of something. Okay, just as a reminder. So for example, let's write out the Kc expression, okay, and calculate the value of Kc for the following reaction. So we've got SO2, remember we brought this one back. Concentration of SO2 is 0.4 moles per dm cubed. The concentration of O2 is 0.2 moles per dm cubed, and the concentration of SO3 is 0.8 moles per decimeters cubed. And obviously we've got our reaction written down there. So our Kc expression, I think really this bit should be put a little bit earlier on in the video, and I'll get that swapped around in the PowerPoint as well. I think this is coming a little bit late, so this really should be towards the top, but you will have seen Kc expression anyway at AS. But the Kc expression is Kc equals SO3 squared divided by O2 squared multiplied by SO2 squared. So remember the powers here, these numbers here, okay, these ones here are actually related to the number of moles in the reaction here. Okay, so let's put the numbers into our calculation. So Kc equals 0.8 squared divided by 0.2 squared, 0.2 multiplied by 0.4 squared. So our Kc value here is 20. Okay, so we just put all the numbers in. Remember to square the numbers. Look at the number of moles in your equation, and that's the power that you put on your Kc expression. Okay, so what we're going to do is we have to write the units as well. The units of Kc vary depending on the reaction that we're looking at. So really straightforward. You might have seen this. You might have seen this already. But what we do is we write down the units that we have for the reactants that we're using. So you can see here we've got 0.8 squared. So because it's squared, we write the units out of concentration twice: moles per dm cubed, moles per dm cubed. We also have 2 lots here. So we've got a 1 to the power of 1. And we've got 1 to the power of 2. So if we add all them up, that's to the power of 3 in total. So we write that out 3 times. So that's going to be moles per dm cubed, moles per dm cubed, moles per dm cubed. And effectively what we have to do is we cancel out the units, we cancel them all out, and then any that are left at the bottom are inverted, and we flip the sign. So let's have a look. So you can see we're cancelling out them ones there. We have moles per decimeters cubed on the bottom, so we invert that to bring it up to the top. So what that means is we have mole to the -1 dm3. So we just change the signs of our units. So you can see there, mole to the -1 dm3. Okay, so not too bad. I think the key thing here is just making sure you're putting your powers in there, and that you are, when you're calculating it, you are putting your powers in there too. That's the most important thing. And obviously the units as well. Remember, if the units are on the bottom line, you invert them. If the excess units are on the top, you don't need to do anything. You literally just write down the units that it says on there. Okay, so let's have a look at the equilibrium constant, and we're going to try and, or the equilibrium concentration, and we're going to try and link this to experimental values or practical wise. So to find out the concentration of a substance at equilibrium, so remember that equilibrium constant is using the concentrations of substances at equilibrium. Okay, so in order to work out the concentrations of them, we need to know methods which will not affect the equilibrium position. Okay, so this is how we're going to work out, how much do we have of each of these chemicals or reactants and products, how much do we have at equilibrium. So colorimetry is one example of doing this. So if we have a colored substance in the reaction, then colorimetry can be used, and we can look at the concentration of a substance at equilibrium using colorimetry. So the color will absorb a particular wavelength of light, and this can then be used to determine the absorbance of the wavelength of light of the reaction at equilibrium. So we can say, right, how much, what's the absorbance of that light at equilibrium at that point. And what we do is we use a calibration curve to work out the concentration of the colored substance. So we plot, basic calibration curve is where we plot known concentrations, we make up fixed concentrations and plot them on a graph so we get a straight line. And then what we do is we take our test sample here, as you can see in this diagram here. So let's say this was a reaction that was let to reach equilibrium, and then what we do is we measure the absorbance, which will read on there, and then what we do is we use that figure against our calibration graph to work out the concentration of our substance at equilibrium. Okay, the other way is using pH. Now pH can be useful if your reactants or products have different pH values. So for example, if we're going from acid to neutral, so if it's a neutralization reaction, for example, and so a pH meter can actually be used to determine the pH at equilibrium, and then we can use the pH equation, and you see the oceans topic that we did that in, to calculate the concentration here. Okay, so you can see there's various ways in which we can measure the concentration of our substance at equilibrium in terms of in a practical sense. Okay, so now we're going to use that Kc, okay, the Kc value that we've seen there, to find equilibrium concentrations. Okay, so we can work out an unknown concentration at equilibrium using a Kc value. Okay, so let's have a look. So a reaction took place at equilibrium. And at equilibrium, equilibrium was established. Let me get my words out. Okay, so equilibrium was established. At equilibrium, the concentration of ethanoic acid is 1.8 moles per decimeters cubed. Ethanol was 3.2 moles per dm cubed, and the value of Kc is 3.5 at 25 degrees Celsius. Obviously, that's being given to you. So calculate the concentration of the products at equilibrium. So you can see here that we've got our reaction here. This is an esterification reaction. So we're taking a carboxylic acid, as you can see there, reacting it with an alcohol, and we're going to form an ester plus water in this example here. So the first thing we need to do is write down our Kc expression. So our Kc expression, remember, is products over reactants. So products is going to be our ester, which is here, and then we've got water, which is a product, and then we've got a carboxylic acid and alcohol down at the bottom there. So then what we need to do is we need to actually put our numbers in that we've got. So here they are here. So we have the value of Kc as 3.5, so we already have that value there. We don't have the concentration of the ester or the water, but we do have the concentration of the acid and the alcohol, so we write them down in there. So that's what we've got so far. Now we need to rearrange this, because remember what we're looking for is the concentration of the products at equilibrium. So we're looking what their concentrations are. So we rearrange that and we get this, 3.5 times by 1.8 times by 3.2. So you can see here that our concentrations of both of them are going to be 20.16, the concentration of both of these substances. Now the key thing here is that actually the concentration of this is going to equal the concentration of this, because they're both formed from the same reactants. So therefore what we can say is that they equal the same. And so for that reason, we can then square root the answer that we've got there, because this is the concentration for both of them. Square root that answer, and we get an answer of 4.49 moles per decimeters cubed. So this would be the concentration of both our products. So we've got our ester, which is 4.49 moles per decimeters cubed, and we've got water, concentration of water, which is also 4.49 moles per decimeters cubed. Okay, so you see there, it's just about putting the numbers in there, rearranging it, but don't forget, and there are people who do this, and it's such a silly thing to forget, but it's to square root it at the end, okay? You've got to square root it to get the concentration of the individual products on their own, but the assumption we can make, like I say, is the concentration is the same, and we can make that assumption because their molar ratio is 1:1 in the actual initial equation here. Okay, so just coming on to the final bit. This is a bit more complicated, this. So we're going to be looking at the concentration of a species in equilibrium and how that can be worked out before actually working out Kc. So we're going to be looking at something, and I use this method called an called ICE. But you may use a different method when you see this here. I just like to, if you see any of my other videos, I like to keep it methodical and precise and make sure that we're accountable for every step that we're doing. So let's look at an example. So nitrogen dioxide decomposes according to this reaction here. So you can see here that we've got nitrogen dioxide forming nitrogen monoxide and oxygen. And so we have 33.2 grams of NO2 was heated in a vessel with volume of 9.65 decimeters cubed at 450 degrees Celsius. Okay, and 6.88 grams of O2 were found in the equilibrium mixture. We need to calculate the value of Kc. Okay, so what we need to do is work out the value of Kc in this reaction here. But what we've been given is masses at the start. We've been given some of the masses of products as well. So we've got a range of different data here. So it's not just as straightforward as just putting it into our Kc expression and working out the value of Kc. Okay, so use the acronym. Like I say, we're going to use the acronym ICE. So initial moles, change in moles, and equilibrium moles. Okay, so ICE. Okay, so the first thing we're going to do, and I draw this table. I draw this table here, which is initial change in equilibrium moles. And then what I do is I put the number of moles of the substances at the top here. So we've got NO2, NO, and O2, and I put the molar ratios in front of them as well. And basically what we're going to do is we need to work out what is the concentration of these at equilibrium, so we can then work out Kc, which we'll look at here. So the first thing we need to do is we've been given moles and masses and volumes, etc. So we need to get concentrations here. So the moles of NO2, which is mass over MR, remember. So the mass is 33.2 grams divided by the MR of NO2. So it's 14 plus 16 plus 16. And that gives us 0.72. So that's the number of moles of NO2 right at the start of the reaction before we actually reacted it. Our products are 0. We haven't actually produced any products, okay, because we wouldn't have. We have loads of reactants, but no products at all because we haven't actually started the reaction. So then what we need to do, and we can see here that we have no moles. This is moles, remember, not concentrations. We have 0 moles of oxygen. But it says here that we actually have 6.88 grams of oxygen were found in the equilibrium mixture. So at equilibrium, we had 6.88 grams. Now, what we can do is work out the number of moles from that, because we've got the mass and we know the atomic mass of oxygen. So that's what we're going to do. So there we are. So the number of moles in this case is going to be 0.215. Now, the change is going to be plus 0.215 because we're producing the product. So we're starting with nothing at the start of the reaction and we're producing the product. So the change is plus 215. So then what we're going to do is we're going to use the molar ratio to work out the changes for the other species. So remember that products will increase. So these are your two products here. These will increase in value and your reactant will decrease by the same amount. Now you can see here that we've got a 1 to 2 or 2 to 1 ratio. So if this is increased by 0.215, then this will increase by twice that amount. So let's have a look. So there it is. So it's 2 times by 0.215 because it's a 2 to 1 ratio. So the number of moles at equilibrium is going to be 0.430. And then likewise, we can do exactly the same for our reactants. So a reactant is going to be, it's a 2 to 1 ratio again. So it's 2 lots of 0.215, but this time it's going to decrease by that amount because this is being used up. So it's 0.72 minus 0.430, and that will give you 0.29. Now, what we have here is the equilibrium moles, so that's perfect. But we can't use moles, we've got to use concentration in our Kc expression. So we're going to use each of them to work out the concentrations of each of our substances. Now we know the total volume here is 9.65 decimeters cubed. So they've given the volume here. So what we do for each one of them is work out the concentration of all our reactants and products by doing number of moles divided by volume, and that gets us the concentration. If your volume's in centimeters cubed, make sure you convert it to decimeters cubed. Okay, so now we've got our concentrations, we can then finally put this into our Kc expression. So our Kc expression, remember, is products divided by reactants. Okay, so that's it there. We put our numbers in that we've just worked out there. Remember to square some of the numbers because they've got a value of 2 in the molar ratio. And then we get a value of Kc, in this case, to be 0.050. Now we need to work out our units, so there's our units there. So we've got 3 lots of moles per dm cubed on the top and 2 on the bottom, so we cancel them out. And we have our remaining one that's left, moles per dm cubed. Now because that's on the top row, we don't need to do any inverting, so we literally just write that in there. So that's moles per decimeters cubed. Okay, so you can see there's a lot of different parts to that. I like to use, like I say, the ICE table, initial change in equilibrium. You might have a different method. As long as it comes out with the same answer, that's fine, and you can show your working for the examiners. So, but it's just trying to be methodical and see what's actually happening. Okay, and that's it. So that's everything that you need to know for equilibrium and sustainability for so within the CI topic, the chemical industry topic. Like I say, there's a full range of videos for salters for year 1 and year 2 on Allery Chemistry YouTube channel, as well as generic whiteboard tutorials as well. So there's quite a lot in there. Go and have a look. It's all for free. All I ask is you please hit the subscribe button. That'll be absolutely fantastic. And also, if you want a copy of these, then you are more than welcome to have a copy of them. We click on the link in the description box below. We'll be able to purchase them. They're great value for money, and you can even print them off and write all of them and do whatever you want. Right, that's it. Okay, bye bye.